Thank you very much for the kind introduction, also the invitation to speak. So it's my pleasure to be here today to tell you a little bit more about FHE. So I'm really going to start from the beginning of what is FHE, and then the focus of the talk is going to be around how can we actually apply it, how far along the journey towards practicality are we with this technology. So yeah, the talk will be in 3 parts. So I'll start with some general introduction, then we'll speak about some specific applications and give some details about how they work. And then finally, I'll talk about some kind of limitations or challenges to making this more widely deployed. Okay, so I understand that you've heard about FHE before, which is great, but I will start from the beginning nonetheless, just to give you a refresher. So what is homomorphic encryption or fully homomorphic encryption? So it's this cryptographic primitive that, in addition to the usual key generation, encryption, and decryption operations, also has this evaluation algorithm. And it permits this very cool functionality whereby the eval algorithm takes as input a ciphertext and some description of a function, and the result is a ciphertext again that encrypts the evaluation of the function on the underlying plaintext. So here in this picture, the kind of yellow box is saying ciphertext. And so what this means is the purple client can outsource the computation of F on their private data X to this cloud server. And the cloud server doesn't know their data X, nor does it learn the output F of X. That's sent as the output ciphertext back to the client, and the client is the person with the secret key, so they're the one who's able to decrypt. So already you can imagine that if we can do this, then we can solve all kinds of problems relating to outsourced or delegated computation. So that's really cool. And in a manner that preserves the privacy of the client's data X. So I want to give a couple of slides of wider context. So fully homomorphic encryption fits within a wider class of technologies called privacy-enhancing technologies. We've also seen co-ed as well, as maybe another way to describe some of these. So let me just introduce some of the others as well. And yeah, all of them are protecting privacy in some kind of way. So for homomorphic encryption, it's this idea of computing on data, but the data is kept private, so the client gets some additional privacy property compared to usual delegation of computation. Differential privacy is another kind of pet that gives a different notion of data privacy. So a very high-level description of differential privacy is, imagine you are computing some sort of statistic on some data set. The idea is that the output statistic does not depend on any particular input of the data set. So here illustrated in the picture is this idea that this is 2 data sets that differ in just one point, so maybe the data relating to just one person, and the output statistic looks the same. So we can conclude from this that we can't infer anything from the output statistic of any particular individual. So that's another way in which data privacy of an individual could be preserved. There's also these secure hardwares, trusted execution environment type technologies. There the privacy or the security is coming from the fact that the secret data is processed on a particular enclave that's then like separated, not accessible from other parts of the processor. So that's another mechanism by which privacy could be ensured. There's federated learning is another example. This is a kind of different paradigm to usual machine learning training, where instead of lots of users having to share their data to one data set which does all the training, there's some local training on many individual users. And this way a machine learning model could potentially be trained, but in a way that each individual person does some training locally and potentially preserves the privacy of their local data. And one that I'm sure you'll be familiar with as well, maybe you're familiar with all of them, multi-party computation. So this is describing a setting where many users want to jointly compute a function. Each of the users has some private data. At the end of the protocol, they maybe communicate with one another and maybe do some local computations. At the end, each of the users gets the output, f of xi, where xi's are all of their inputs. But they only learn that output and nothing more, except what can be deduced from it, about the private inputs of the other parties. So yeah, FHE is one of these many privacy-enhancing technologies. And I think, practically you can also think that maybe to achieve a particular privacy goal or a particular security goal, you may want to actually combine one or more of these paths. Okay, another zooming out context thing about FHE is it falls within post-quantum cryptography, which is very nice. So this is the branch of cryptography for which we believe there's security even in the presence of quantum computers. So not only are the underlying problems classically hard to solve, but also we believe they're quantumly hard to solve. And you may be aware there's several classes of post-quantum cryptography, code-based, hash-based, and so on. And FHE is falling within lattice-based cryptography. So kind of when we're working with FHE, we're getting this post-quantum security inherently, which is very nice. Okay, so I've given the kind of high-level picture, so now we'll go more into details about FHE itself and then its applications. So how would we practically achieve fully homomorphic encryption? All we need is two operations. So we need a homomorphic addition operation and a homomorphic multiplication operation. So the homomorphic addition operation takes as input two ciphertexts that encrypt X and Y respectively, and the output is a ciphertext that encrypts X plus Y, so the plaintext addition. And similarly, the multiplication takes as input a ciphertext encrypting X, ciphertext encrypting Y, and the output is a ciphertext encrypting X multiplied by Y. And with this, we can build arithmetic circuits on ciphertexts and, compute whatever function we like in principle. And so, you can also think to yourself, it's kind of natural to think about if you want to outsource a computation and evaluate it with FHE, you really want to think about how you can describe it in this combination of additions and multiplications. So, for example, like a polynomial evaluation, which could potentially be a limitation in practice if your function doesn't naturally have this type of description. Okay, so there's different flavors of homomorphic encryption. So I'll define them all. So partially homomorphic encryption would be describing a scheme that has either one of homomorphic addition or homomorphic multiplication, but not both. Textbook RSA is an example of a partially homomorphic scheme that I'm sure you're familiar with. Then we have somewhat homomorphic encryption. So this is a scheme that supports homomorphic addition and multiplication, but only up to some limited extent. So either you can think about it as supporting the evaluation of a polynomial of a fixed degree, or a circuit of up to some fixed depth. So you can do some homomorphic operations, but you're limited in some sense, and I'll explain why shortly. And then fully homomorphic encryption is what we would really like. In that case, it would be you could support whatever computation you like, so arbitrary computation on encrypted data. So this is what would be really desirable. And what Gentry noticed in preparing the first FHE scheme, and we still use this paradigm today, is that if you introduce a bootstrapping operation, so-called, you can go from an SHE scheme to an FHE scheme. What is bootstrapping? No details today, only high-level description. But basically the idea is you homomorphically evaluate the decryption function. So you go so far through your circuit as you can, then you have a ciphertext that you can't do much more with, then you homomorphically evaluate decryption, and it's like resetting back to a fresh ciphertext, and then you can carry on. So it's a really cool technique. Why do we need this? Why can't we just compute as much as we like as we go? So all of these homomorphic encryption schemes, the ciphertexts have this inherent noise, which is needed for security. But it really grows as you move through operations, particularly as you do more multiplications. So after you've done a few multiplications, the noise is typically very large, and if it is ever too large, then it can be the case that decryption will fail. So you've lost the functionality. So you really need to carefully understand how the noise is going to grow and bootstrap at appropriate times if you're doing FHE, so that you can actually correctly evaluate what you want to evaluate. I say if you're doing FHE because there are some settings in practice where you would actually only restrict yourself to a somewhat homomorphic encryption setting, And in this case, if you know in advance what you want to compute, it's not too large of a computation. You can choose big enough parameters that everything fits within FHE without having to bootstrap. So both paradigms are possible. And it depends on the FHE scheme, which is the more practical, I would say. Okay, so I hinted that FHE schemes were based on lattices. Let me make a more explicit statement. So insert your favorite FHE scheme in purple, so e.g. the BFE scheme is a widely used one. And BFE is in CPA secure if learning with errors is hard. So hopefully these words are meaningful to you. If not, let me give an analogy. So a different scheme, RSA OAAP, completely different, just regular RSA encryption with good padding, is in CCA secure if factoring is hard. Yeah, so hopefully that's clear. So yeah, this notion of security being mainly in CPA security, it's kind of interesting because it does depart from kind of other encryption where CCA might be more exactly what you desire. But here we kind of need there not to be CCA in order to have this malleability, so we can actually manipulate the ciphertext to add and multiply them. But what in-CPA security does give us is that the ciphertexts look random, so it is giving you the property that you want, that a server seeing a ciphertext can't look at the ciphertext and deduce the client's underlying data. So yeah, you can't tell if it's an encryption of 0, encryption of 1, encryption of whatever. So yeah, this notion is not as strong as in CCA, and that's kind of inherent because we do want some malleability. But there are several intermediate security notions, and more research is coming in to look at these different intermediate notions. One of them you might see if you're looking in the literature is in CPA-D, which is a notion that's giving a kind of restricted decryption oracle to the adversary as well. And such notions have been shown to be potentially relevant in some applications. So yeah, this is still an area of ongoing research, but pretty cool. Yeah, but for the main part today, we're I think, thinking of in-CPA security. Okay, and then what's going on over here with learning with errors? So perhaps you've seen this problem defined before. This is one of the main hard problems underlying lattice-based cryptography. And very briefly, what's the problem? So a learning with errors sample consists of a public matrix A and some vector B that's constructed as follows. So there's a secret vector S and some error E, which is also secret, and B is formed as A times S plus E, modulo some modulus Q. So the search learning with errors problem is asking you, given this A-B pair, can you find the underlying secret S? And yeah, for a very high level picture, because I'm not giving lots of details today, you could think that like S could correspond to the secret key in a symmetric FHE scheme. And AB is an encryption of 0. So then when you have that, it's almost immediate how the in-CPA security argument would make sense. Okay, and then this error E that's coming like inherently from the security assumption is the like root cause of this noise that I mentioned. So yeah, there's kind of no way to avoid it because if you didn't have it, then you'd be able to just invert A and like multiply by A inverse on B to get S. So you definitely need noise in learning with errors for it to be hard. And so consequently, you need noise in FHE schemes, and consequently, when you multiply, the noise is really going to grow. Okay. Okay, so yeah, this is a history slide, but I've also called it Journey Towards Practicality, because maybe we're moving towards a world in which FHE is practical. So how has the journey looked so far? So actually this problem was open for a long time. It was already proposed in the late 70s, like, can we actually build FHE? And it wasn't until 2009 that someone showed that you can, so showed by Craig Gentry. And around this time, there were other early schemes alongside Gentry schemes. They were very cool theoretically, so a huge breakthrough, but possibly not even implementable, very slow. Yeah, many orders of magnitude slower than plain text computation. So as a result of that, it wasn't for another couple of years until we started seeing literature that looked at possible applications of FHE. And then things really started to accelerate. So in 2012, we had what's so-called second generation schemes, and examples of these include the BGV and BFV schemes, which are still widely used today. Things continued. There were these so-called third generation schemes, starting with GSW, moving through DM, CGGI. And alongside this was also the phase where things started to be implementable. So even so far as to have libraries that were open sourced and people could use to start potentially developing FHE even further. And yeah, what's the reason for the naming of these generation schemes? I guess it has to do with kind of different multiplication behaviors or different supported plain text spaces, but it's not very important for the rest of the talk today. Then in 2015 was a very exciting moment because we really started to have a situation where bootstrapping became kind of fast, so maybe like 1 second or 0.1 seconds to evaluate your bootstrapping for the third generation type schemes, which still have the fastest bootstrapping today. So that's really exciting. It starts to be the case that FHE is really practical, perhaps, or could be really practical. 2016, there was another big moment because a fourth generation scheme was proposed called CKKS. This was kind of a fun scheme because it allowed more direct computation on real data, which might be the kind of data you might see more in practice. So yeah, we'll see later for some of the applications why this might be very important. Yeah, the community continued developing implementations alongside these schemes, and it was even getting to the point where it was felt that this could be the kind of technology that could be sold in products to customers. And so I think motivated by this, a consortium was formed called homomorphicencryption.org, which consists, it's still active, of industry partners, also governmental partners, also academics, trying to work towards standardizing some FHE schemes in order that there's better infrastructure for really bringing this into practice, bringing it to market, and so on. And yeah, so really it was around the same time that it was not only like large corporations that were investing into FHE, but even startups were springing up, bringing HE applications towards the market. So we're moving more and more towards practicality, commercialization, at least the idea that this could be widely deployed. So already for the last few years even. So homomorphicencryption.org was a community effort, but more recently, in 2020, there was a formal effort through a standardization body, ISO-IEC, to standardize certain FHE schemes. So the standards are still being developed, but ISO-IEC standards for 4 of the major schemes, BGV, BFV, CGGI, CKKS, will be available, I think, maybe by 2025, 2026. It's a slow process, developing ISO standards, but it's underway. So yeah, I think we're really in a world where we could start to say that FHE is practical for some applications. And yeah, so I mentioned, the first implementations were already almost, in fact, over 10 years ago. And by now there are many widely available implementations of different schemes. Almost all of them are open source. So I've listed some examples here, but it's certainly not an exhaustive list. And actually there's a reference here for further resources if you'd like to look into any of this in more detail, either the implementations or other resources to learn about FHE. And yeah, so the libraries typically implement a variety of schemes. All of them are the schemes that are being standardized. So it's kind of, at this moment, it seems people have coalesced around particular schemes, although it's not to say that there's not research on new FHE schemes. And I think there's space to keep doing that as well. And who has been developing these? You'll see kind of big name companies there, IBM, Intel, Microsoft. So they've certainly put a lot of funding into FHE, but also there are plenty of startups represented here in the list as well. Crypto Lab, Insight, and so on. And yeah, definitely not an exhaustive list, but just to give you an idea, there are many, actively developed libraries implementing these schemes. So you can go ahead and play with them today if you wish, or in the future. All right, so that's a general introduction to FHE, so it's a good point to pause for questions if there are any. If not, then let me move on to the next part of my talk. Okay, so I want to tell you today about applications of FHE in general, and also look at some specific examples of applications that have been reported in the literature or even deployed practically, or I'll clarify what I mean shortly. So yeah, there's really, you're limited by the space of a slide, what you can say the applications are. It's almost impossible to list all possible applications, because there's literally so many ways you could imagine how outsourcing computation on private data or data sharing could be valuable to different entities, and may not be possible without such technologies as FHE, because the data involved could be sensitive or private, and therefore subject to data protection laws and so on. So yes, some possible applications though, to be concrete. So one direction is privacy preserving machine learning. This is a very actively researched application area, and that's both on the inference side and on the training side. So we'll speak in a little more detail about inference later on, but let me say about the training also. So the idea there would be, instead of having just a plain text training set and you train your machine learning model over it, you could, in principle, have an encrypted data set and use FHE to homomorphically evaluate the training. And this way, it could potentially enable you to train a model on private data, maybe from multiple individuals. So that could be another way to unlock potential from data. There's two related primitives called private set intersection and private information retrieval. So these can be in themselves useful applications in practice, but also we can think of FHE being here, its application is as part of building a wider cryptographic primitive. So certainly there are plenty of applications just in cryptography itself, and some of the interesting primitives you could build could be PSI or PIR. We're going to see a PIR example as well. Something else that could be a nice application of homomorphic encryption, and it's quite easy to explain, is electronic voting. So I don't have more slides about that, so I'll say something about it now. So yeah, you could imagine a very simple type of election where there's two candidates, candidate A and B, and you want to count the votes of an election, but you don't want any individual's vote to be made public or disclosed to anyone else. So you could imagine then in a HE scheme, if a person wished to vote for candidate A, they can encrypt the vector 1-0, and if a person wished to vote for candidate B, they could encrypt the vector 0-1. And then we can take the encryptions of all of the votes and homomorphically add them, and the result of that is going to be a vector which in one part is the total number of votes for candidate A, and in the other part is total number of votes for candidate B. And so maybe the election authority can decrypt that ciphertext, and the result is the kind of result of the election. You could read off from this which candidate had the most votes and then would win. But in this way, like no intermediate person who's observing this network could see what any individual's vote was, because it was a ciphertext. And obviously the NCPA security means that you couldn't tell if it was an encryption for candidate A or an encryption for candidate B. So that's really nice. But yes, there's lots of other things to take into consideration when developing electronic voting. It's also a whole research area by itself. And yeah, other kinds of processing of data. We could think of evaluating some statistics on private data. It's in a way similar to the machine learning example. And yeah, there are many more applications possible. And also, as you can imagine, there's many different settings where these applications may be beneficial. So I'll just highlight some of the commonly referenced ones, but again, there's many more. So one setting where there might be very useful insights to gain from data, but the data is very, very sensitive, is something like genomic data or healthcare data relating to individuals. So you may yourself wish to know, does my genetic code imply that I'm at higher risk for some certain diseases? And this you may be very interested to find this out and are even willing to work with some external company or healthcare provider to try to determine this. But like sharing your entire genome is a very sensitive thing. So maybe you'd rather do this via homomorphic encryption. That way you're encrypting your genome data and also the result of like whether or not you're at risk of getting some particular disease or developing it in the future. But this way you could actually find that information out. Whereas before maybe the fact that you would have to share your genomic data makes you not want to even try to find it out. Similarly, healthcare settings, you may have blood test results or other kind of like health-related data points that could potentially be combined to determine whether you're currently suffering from some disease or you're about to develop it. And again, depending on the context, you may not wish to share this data with multiple parties, or it may not be possible to share this data with multiple parties due to various laws. So again, it's this kind of idea of potentially unlocking further information that could be useful to people, but which one can't or people don't want to currently do this kind of processing. And then in the finance setting, and yeah, my next slides will go into this in more detail, some of the cited possible applications have included things like anti-money laundering or otherwise detection of different kinds of fraud. And yeah, we're going to see this right now in my first detailed example. Okay, so I've taken this case study from the ICO, which is the UK Authority for Data Protection. So this image and actually the full details of the case study are available directly at these links, so please read them if you'd like more information. But I'll talk through the main idea. So this setting is using homomorphic encryption for data sharing, and it's particularly focused in a finance type setting where there's multiple parties, each with different data sets, and they may wish to get some kind of insight from their joint data. But, you know, like, for example, you can think of these participants as banks or financial institutions, and typically these institutions would not share with each other if they had information about account holders that were related to fraud, again, because like one can't share data about like your account holders because it violates privacy laws. So yeah, so a bit more detail about who these people are in the picture. So there's this consortium of entities, maybe different financial organizations like banks, maybe law enforcement agencies are involved as well. Each of the entities has their own data set of customers or other data. And maybe one of them is a specific user in the example who wants to find out information from the other participants' data sets that's useful to answering a question that they have. And there's also a central entity here called the hub, whose role is to act as an interface between the user and the other consortium members by forwarding on the query and then aggregating the responses from each of the other participants and sending back to the user. So here an example of a query that a user might have in this context is the user is another bank. Some named person has approached this bank to ask to open an account, and the user bank wants to know, is this person connected with any fraudulent activities? So they could ask a query to each of the other participants in the consortium. Does this named user have any accounts with you that have any fraud flags? Like, what is the total number of fraud flags associated with this named person? And obviously, we can't share the name of that person in clear text, but using homomorphic encryption, we could ask this query in a way that protects the identity of this person. So yeah, the user creates that encryption and sends it via the hub, who sends it on to all of the other parties. Each party then locally, homomorphically evaluates this query that the user has requested and gets some output ciphertexts. These are sent back to the hub, who aggregates them into one output ciphertext, and that's sent back to the user. So still it's encrypted, and then obviously the user is the person with the secret key, so they're the one who's able to decrypt, and they find the aggregated result, which in this example could be, yeah, this named person has 2 accounts with a fraud flag. So that's interesting. It's helped the user to recognize that this named person has been associated with fraud, and maybe they then don't want to let them open an account with themselves. But they haven't learned kind of whether this is 2 accounts at one other bank, or 1 account at each of 2 banks, or which banks this named person has their other accounts in. So it's been a way for this whole consortium to share information about potentially fraudulent actors in the financial setting without having to share information that they'd rather keep private from either of their sides. Yeah, so any questions about that example? Okay. All right, so I'd like to move on to a different example now, which is more in the privacy-preserving machine learning setting. And this, I think it's a really cool example, because this was one of the early papers giving a concrete application of FHE. And yeah, this was published in 2016, so it's already quite old, but I think it's really cool. So in this paper called CryptoNets, they were interested in homomorphically evaluating inference of a neural network on a particular data set, the MNIST data set, which you may have come across before. So this is a data set used widely in machine learning for training. And it's basically a data set of handwritten symbols that look like digits, so like squiggly 6. And you would then train your neural network model to recognize that this squiggly 6 was actually the digit 6. So that's what the picture would look like if this were done in clear text. So you give assume the model is already trained. So we're talking about inference, so we already have this model, and then we give it a new squiggly symbol, and the model identifies this as the digit that the handwriter intended, in this case, a 6. So the CryptoNets paper was looking at how you could homomorphically evaluate this inference. So what would we do then in this setting? So as the client, we would have this squiggly digit, and we would encrypt it. So here now a green box is encryption. Then we're going to run it through the homomorphic evaluation of the neural network. So that's all in the green box. And then the output is going to be some encryption of some digit that the neural network has decided to classify this squiggle as. And then this result can be sent back to the client, who can decrypt it and see that it was classified as a 6. And this may not seem like so useful, a particular inference to outsource, but like this was an early paper showing that even privacy-preserving inference could be done. So one could imagine the same ideas could be applied to some kind of inference that could be more useful, like, yeah, classifying whether or not you're going to get a certain disease, for example. Yeah, server sends by output, client decrypts. So I think it's interesting to look at how and why this can be done, because it might seem at first sight that a neural network is horribly complicated, and indeed it is. So why should we be able to homomorphically evaluate it, even especially in 2016 when things were further along the pipeline towards practicality as they are now? But actually, this is pretty cool, and neural networks have some kind of nice properties as well. So what's going on in a neural network? Well, any particular neuron has okay, so each of these columns are considered as layers. So there's the input layer where input data gets sent to, and then the final layer is the output layer, which will represent the classification. So here we've somewhere in the middle of the network at some neuron B. How do we know what the value is going to be at B? It depends on all the neurons from the previous layer. So here, A1, A2, A3. And how does it depend on these inputs? Well, it's basically a weighted sum of the inputs, and then a nonlinear function is applied to the weighted sum. There is some term, like bias term, missing here if you're familiar with ML. I'm just giving a simplified description just to give the main idea. So parts of this function are actually very nice to evaluate from a homomorphic encryption point of view, because this kind of weighted average thing, especially if the weights are already known because the network is pre-trained, this is some linear function, is actually nice and easy to compute in FHE because it's very low depth. So this kind of is the kind of application that kind of lends itself very nicely to FHE so far. But then this F function is nonlinear, and maybe it's not at first sight obvious how this is going to be evaluated homomorphically. So what F could be in practice could be like a sigmoid function or this rectified linear function called ReLU, or so on. There are different examples in the literature. And like I was saying earlier, like it's convenient, especially in this CryptoNet setting, which was in the somewhat homomorphic setting, to express what you want to evaluate as some kind of polynomial. So this kind of linear function from the weighted average, weighted sum, that's very easy and natural to encode in an evaluation function. But this sigmoid is not very convenient at all. And so what can one do? One can approximate it as a polynomial. So this will introduce some additional error, but maybe that's not too bad in terms of, like, you could potentially still get something that it classifies closely to how a plain text neural network would classify. And what was really cool about CryptoNets is they just used the approximation x squared. So a very simple nonlinear function. And even doing this, they still got an accuracy of 99%. So very cool. So it shows that it's potentially possible to do this kind of approximation and not lose too much functionality. Yeah, a really cool application. Any questions about that? Yeah. No, but I'm very interested to see it. If you have some comments about it, then.
Homomorphically decide whether the photo contains military hardware or not.
Oh.
So whether it's a tank or a car. Well, it won't say tank car, but it'll say military hardware, non-military hardware. Boat, same boat, frigate, whatever. And they do that on real pictures.
That's cool. Yeah.
So that's, so this is ancient. But now you can do much cooler stuff.
Yeah, thanks, Nigel, yeah.
Whether this will have a high performance impact on, like, training the model, for instance. Let's say you don't have a trained model, that you would need a lot more hardware to train a model with this FHE.
Yeah, thanks for the question. So yeah, you're absolutely right that, like, training will be harder than inference, and yeah, it might require like a lot more computation. You can imagine it would be deeper circuits and so on. So there is literature looking at homomorphically evaluating training, but I'd say it's at a less practical stage than homomorphically evaluating inference. Any other questions? Okay, let's move on to another example. Okay, so I mentioned private information retrieval as a nice example of FHE. So firstly, I'm going to describe what PIR is by itself, and then I'm going to show you how we could use FHE to achieve it. So in this setting, we've got a client and server again. The server has some data set, some database, and each database entry is indexed by some number. And so in private information retrieval, what the client wants is the data at entry I. I'll say the security requirement in a second. And so what they want is the service to send them something back that enables them to receive the data at entry number I. Very simple. What are the goals? So we want this to be private in the sense that the server doesn't learn which database point is being requested by the client. And we want it to have some kind of performance. So one trivial solution would be the server sends the entire database to the client locally just picks the entry that they want. Like this would meet the security goal, but it's very inefficient communication-wise. So that's not desirable. So we want something that can enable the client to get the data that they want without the server learning which data was queried, and without it costing the cost of communicating the whole database. Okay, so in this picture, I've slightly changed my notation because it's then easier to give the explanation. So now these, we have a database of 4 entries, and the numbers in the entries are the actual data values. So we can think the indexes are 1, 2, 3, 4 from the top. All right, so how is the client going to get a particular data point using FHE? Okay, well, let's suppose they want the data in the ith position. Here in my example, I is 3. What they can do is encrypt a vector that has zeros everywhere, but a 1 in the position that they want in the ith position. So here in the 3rd position. So they just transmit this ciphertext over to the server, and by the NCPA security of the FHE scheme, the server doesn't learn from this ciphertext which particular index the client is wanting, because encryption of 0010 looks just like encryption of 1000, etc. But we can take this ciphertext, and the server can homomorphically evaluate the inner product of this ciphertext and this database. And what that's going to give you is an encryption of 0 times 12 plus 0 times 345 plus 1 times 6789 plus 0 times 1011. And it's still an encryption, so the server doesn't know what the result is encrypting, but they've got this output ciphertext that they can send back to the client. And yeah, because we've evaluated an inner product with the zeros everywhere except the 1 point that we want, it's an encryption of the value that they want. And they can decrypt it. So very simple, and also very convenient to evaluate homomorphically because we're just doing an inner product. Again, this is a low-depth thing that's fairly easy to compute. Yeah, and then the client decrypts to get this value 6789, which was the one that they wanted. Very clear. Any questions? Nice. Okay, so this kind of thing is actually being used by Apple, which is very cool. They've recently announced this private caller ID lookup functionality. You can read about it on their blog, and I've also taken this image from their GitHub repo, which gives this example. So here what they're proposing is a mechanism for iPhone users to recognize if someone's calling them, if it's a spam call that's calling them, but in a way that Apple doesn't learn the phone number that is calling you. So what's happening in the example? So we're doing a kind of PIR type thing, but the phone number in this case is going to act as the index to a database. So the database has some phone number indexes and identities associated with the phone number. But this is being done homomorphically, of course, so when the phone is querying the database, they're sending some ciphertext, so it's not clear to the database which particular phone number is being requested. And then on the server side, they do the homomorphic evaluation, which reveals an encryption of this user identity Katie. And this encryption is sent back to the phone. And then you see Katie's business on the left-hand side on the phone screen. So the phone is able to then tell the user, like, oh yeah, this number is Katie. So it's not spam. It's this person Katie, who has a particular business. So yeah, this idea is that then people can detect if they have incoming spam, but they don't have to share the identity of who's calling them at that particular moment with the database. Yeah, so I think that's very cool because it's really showing a practical example and an interest from a large tech company. Any questions about the example? Yeah. Yes, yeah. So yeah, that's a very good question, and one that I don't think is particularly answered. So although they're like proposing this and they've announced this, if you read the GitHub, it's basically saying like not necessarily to be used in production, like example only. So not clear to me how well this would scale or how they're going to maybe work towards scaling this in case it doesn't. But yes, good question. Say again, sorry? Oh yeah, that's true. Yeah. Yeah, that's a very good point. There's like different ways you could send more ciphertext to like reduce the amount of computation that's done and so on. So yeah, I've explained it in a very simplified way, but that's absolutely right. There's quite a lot of literature trying to improve this as well. Okay. So so we've seen some examples of some applications that we could say are perhaps practical or perhaps moving towards practicality at least. So what else is out there? So there are a couple of recent white papers that try to like summarize the state of affairs as it relates to practical applications of FHE and PETs more generally. These two reference documents are at least a year old, so yeah, they may not contain the newest applications, but still are very interesting. And what's typically been seen is that things that involve partially homomorphic encryption have been reported, and this is because they're typically a lot more efficient than fully homomorphic, so that's to be expected. But there are some other SHE or FHE applications besides those that I've mentioned that are at a pilot project stage or proof of concept. Even Nigel gave an example of one just now in the questions. My view would be, I think it's shared by others, that perhaps other PETs such as MPC or federated learning are more along the way towards practicality than FHE. But still we see FHE is definitely getting there. And because I think it's interesting to like look at what are companies actually trying to do, unfortunately, they're not always very open about exactly what they're doing. So here is a definitely incomplete list of FHE startups, and here I'm only listing ones that are offering like evaluation as a service. So there's other types of startup working in the FHE space, for example, working on hardware development and so on. So not trying to exclude them on purpose, just kind of looking at like what kinds of functions can actually be evaluated in practice that customers actually want. So this is kind of my question when preparing this table. So we can kind of see some trends in what the companies are offering. It's typically either or both of privacy-preserving machine learning applications or blockchain applications like secure smart contracts. And we see, a couple of examples of like combining different PETs. So for example, Tune Insight is looking at kind of combining FHE with federated learning. So that's also pretty cool. Seeing a lot of work towards privacy-preserving ML and secure smart contracts. But not a lot of details about what is actually being evaluated, I'm guessing because they're trade secrets or they can't actually reveal what the customers are requesting and so on. So that's at least a partial picture of what's going on. So that brings me to the end of my part about application. So it's another good point to pause for any questions if there are any. Yeah.
So with regard to these private information of people, how can you mitigate the fact that you could just ask any information from the database? Like that is not relevant to the database.
Yes, so you're kind of asking two questions there. So for one thing, yeah, it's like the server doesn't know what is being requested, so they have to kind of trust that the client is sending like a genuine encryption of like a genuine vector that's like lots of zeros and ones, and that's like identifying which data point that they want. So I guess you could argue that side by saying like the client is the one who wants to access the data, so it doesn't make sense for them to give a malformed ciphertext. Well, maybe. If it could make sense to argue that there's a reason to believe the client is behaving honestly.
They're not necessarily about that malformed ciphertext, but they are just interested in what is in the database.
Yeah. Yeah, so these are kind of like database query type things. Yeah, so in my example, the database wasn't encrypted, but you could have it that the database is encrypted, and then maybe it makes it harder for the client to glean information that way. But yeah, there are kind of works that look at querying databases and show that somehow the database can be partially recovered. Yeah, so I guess it depends on the specific context. And then your other question kind of is in a way saying like, well, what if the server misbehaves? And I have a slide about that. Yeah, so thanks for the question. Does that answer? Yeah, great. Okay. Okay, yeah, that sounds really interesting. Yeah, I'll take a look, thanks. Okay, then let me move on to the final part of my talk. So some words about like what are the limitations of FHE, or what kind of practical considerations are there when trying to build an application or to kind of deploy FHE for your favorite use case scenario. So please don't read this whole table because it's it's horrible. The purpose of presenting you this table, which is also very small because there's a lot of information contained in it, is to kind of illustrate that choosing parameters for your FHE deployment is a really complicated kind of a problem. So this kind of already limits to some extent how easy it is for FHE to be used. So this is a table kind of listing parameters that are relevant to either security, performance, correctness, or sometimes multiple of these. So let's actually draw them out. So virtually all of them are relevant to how your implementation is actually going to perform. And sometimes like tweaking them slightly can like drastically affect the performance. So setting all of these parameters carefully is relevant for performance. Some of them are relevant to the underlying LWE instance and therefore relevant to the security. So also these have to be carefully selected so that your deployment meets a target level of security. And many of them have to do also purely with correctness. So this is kind of like the problem of how big is my noise going to grow? Am I going to reach the point where if I would decrypt it would fail because the noise is too big? So these parameters also have to be chosen, and these parameters influence the noise, and well, they all influence the noise to some extent. It's extremely complicated. So work has been done to try to aid users in choosing parameters. You can read this paper, for example. And some of them I forgot to say as well. They relate to choices that could be adopted if you want as optimizations. So they're not strictly necessary, but you could choose to do them. So again, this is a question for you when you're developing, like, do I want to do it in this particular way or not? Which scheme should I use could already be a relevant question, or like which library should I use? And it probably depends on the application, which is the best choice. So something else to consider that relates to this issue of correctness is around encoding. So it turns out that typically the plaintext space that's kind of native in your HE scheme is some kind of polynomial ring. So when you're looking on the face of it at issues of correctness, you have your two input plaintext. So this is a very simple evaluation operation, it's just an addition. So we've got two plain texts, we encrypt them, we get two ciphertexts, we do the homomorphic addition, we get the output ciphertext, and then we decrypt it, and we hopefully get the plain text corresponding to the plain addition. So already this could fail at the decryption step if the noise in CAB was too large. Probably if it's two fresh ciphertexts and you add them, it's not going to fail, but just imagine it's a more complicated circuit if you like. But then there's a kind of wider issue. So it might be that the two things you want to add are not polynomial ring elements, right? There might be your actual data is integers or real numbers, so that you've got to also get from your input data somehow to a plain text element. So this is the problem of encoding. There are many solutions to this, approaches to this. There's actually ways you can encode multiple message elements into one plain text, which can give you some parallelism in some cases, which is very nice. But this is another issue which you need to take care of. And then on the other side, when you've got your output plain text, you also then need to decode this to some output element of message space. And decoding may also fail even if decryption has succeeded. So this is another layer of confusion potentially when trying to set up your parameters that this will work. So I think it's, a nice pictorial example of another complication. And then yes, relating to the question from before, so it's a very, very good observation. So you're in this malleable world, it's only in CPA typically. You can manipulate ciphertext. The eval function is manipulating ciphertext. So what happens if the server is somehow malicious and wants to not run the exact algorithm eval and genuinely compute a ciphertext that encrypts f of x, but what if they instead at the end add an encryption of 1, so they've returned you f of x plus 1 instead. So they can definitely do this, and they may do it in a way that the client won't detect. So for practice, this kind of issue of verifiability is really key, and this may make it not suitable by itself in some application settings. So the client may be able to detect this, right? For example, if the client is asking for some probability and the number that comes back is 3, then they know that's not a probability. Obviously, the service does something strange. But if it comes back 0.6 and the answer that was real was 0.58, then maybe nobody realizes that something malicious has gone on. This is a real issue in practice. There are proposals to combine FHE with zero knowledge proofs and so on to kind of prove that the ciphertexts are computed honestly, but this will be way more expensive. So yes, it's kind of inherent from the NCPA security situation. So that may be really a problem in practice. Okay. And let me conclude by kind of giving an idea of our next steps on the road towards practicality. So what is the current research in FHE, because there's still a lot to be done. So so we've already hinted that, or said to some detail, that maybe in CPA is not the right security notion in every context. Maybe in CPA-D is more relevant, or other intermediate notions up to in CCA. Maybe we need to combine FHE with zero knowledge proofs or other techniques to get some kind of guarantees that the server is behaving honestly, and so on. So that's definitely one path for more research. Another wide area of research that's very important is kind of addressing this issue I highlighted of the parameter selection being very complicated, and more generally the scheme selection and the implementation details. It's all very challenging and maybe not accessible to general developers who are not deeply expert in FHE or cryptography. And so work has started towards building compilers that could really take someone from developing, writing code as they normally would, and converting that usual coding and development into, for example, this useful arithmetization of the circuit with the right choice of parameters that means that the library or the compiler can take care of all the parameter selection, and the user can just focus on developing code. And I guess this really would be an integral part of making this truly widely deployed. Yeah, so lots of work in that direction. There's work looking at integrating FHE as part of more PETs to get a solution for particular application context that really meets the security and privacy requirements of that application. Perhaps FHE by itself won't suffice, so yes, it's important to look at how FHE can be combined with other PETs. Lots of work has been going on towards hardware acceleration of FHE. This is a really cool and important direction because it can probably give speed-ups of maybe 100 times or more. So developing specific hardwares that FHE can run over more efficiently, similarly to how we have like hardwares for AES and so on. So that's a really important direction. And yeah, bootstrapping is also very important if we want to move from the SHE world to the fully FHE world. Then it's important to keep doing work to improve bootstrapping across all schemes. And so, yeah, for certain schemes, bootstrapping is still slow, maybe prohibitively slow. So it's important to keep trying to find new ways of improving bootstrapping as well. All right, so I'm almost done, but there's time for a shameless plug. So if you enjoyed this explanation of cryptography today at an introductory level and hopefully accessible level, then you may like to purchase the second edition of Cryptography, A Very Short Introduction, written by myself and Sean Murphy. So the first edition was written by Sean Murphy and Fred Piper in 2001, and a new edition will be published in 2025. You can pre-order it now, so please consider getting a copy for yourself, your friends and family. Yeah, and thank you so much for your attention. I'm happy to take any questions.